Hello class, welcome to the final segment in lecture 23, and in this final segment we're going to talk a little bit about how to diagnose storm modes, that is determine whether you're going to have isolated modes or linear storms on a potential severe weather day. So that's going to be the main topic for this segment, and let's go ahead and dive right into it. So there's two main factors that you want to consider when diagnosing storm mode. How much upward motion is there, and how is the wind oriented relative to your boundary that's initiating thunderstorms? So, as we sort of alluded to earlier, if you've got a wind vector that's running perpendicular to your surface boundary, that's going to have a much higher chance of producing isolated thunderstorms. This is not going to guarantee that you're going to have isolated thunderstorms, because if your vertical motions are too strong, yes, you're going to have this flow that's perpendicular to the boundary, but if your motions are too strong, you're going to have too many thunderstorms going up, and they all might start interfering with each other, but at some point they're probably just going to all merge into a massive line anyway. So just having mean flow that's perpendicular to the boundary is not going to guarantee isolated thunderstorms, but if you want isolated thunderstorms, this is one of the things that you want to see in the atmosphere. In the case of linear storms, which are storms that rapidly become linear after developing, you want a flow pattern where the wind is running parallel to the boundary that's initiating the thunderstorms. And this is also a flow pattern that you would ideally want to see if you want a flash flooding event. So if you're going to have thunderstorms that are not producing a lot in the way of cold downdrafts, they're what we would refer to as being cold pool deficient. If you've got sort of a flash flooding setup with a flow pattern that looks like this, that means you've got potential for training thunderstorms, which is a potential for thunderstorms to all track over the same area as they move with the flow pattern aloft. But in either case, you're going to end up with linear thunderstorms. That is a big line of thunderstorms potentially as they develop along this frontal boundary, whatever it might be. And ideally for isolated storms, you want weak forcing. And of course, there might come a point where your forcing is going to be too weak, because if your forcing is too weak, then you might not get any thunderstorms forming at all. So there's a delicate balance that you have to strike to get isolated thunderstorms, because if your forcing is too strong, too many storms go up and they become linear. But if your forcing is too weak, then you might not get any storms developing at all. So there's a delicate balance that you have to achieve to get enough isolated thunderstorms to get a very pronounced severe weather event like a tornado outbreak. So those are the main two mechanisms, but you can sort of extend the idea of forcing to also the role the cap plays. So one of the roles that the cap can play in the planes is it can limit the number of updrafts that go up. And again, this kind of goes back to what we were just talking about with the idea of weak forcing. If you've got cap, which is again that layer of warm air that rests above the ground, which prevents thunderstorms from going up in the first place, if that cap is too strong, none of the updrafts are going to be able to penetrate it, so you're not going to be able to get any thunderstorms developing at all. But at the same time, that cap can limit the number of updrafts that penetrate the cap, which it gives you a higher chance at achieving isolated storm modes, which also have a higher chance of becoming supercells. And in the case of linear storms, a lot of times the linear environments typically have either no capping or very weak capping, which allows basically any thunderstorm updraft that goes up will be able to achieve positive buoyancy, reach its level of free convection, and then develop into a thunderstorm. Now, you can get isolated thunderstorms with a weakly capped environment if your vertical motions are sufficiently weak. But if you have a strong cap, then you want stronger vertical motions to even penetrate the cap in the first place. So to get a tornado outbreak or a large family of supercells, there's this really delicate balance that you have to achieve. You want vertical motions, but you don't want too much vertical motions. And you also want cap, but you don't want too much cap or maybe even too little cap to achieve a nice tornado event. And another thing that can help with creating isolated thunderstorms is you have some sort of prefrontal lift or prefrontal forcing, so as you have upward motions that are occurring well ahead of the main boundary. So in the previous graphics that we've shown, which have the two cold fronts here, by prefrontal forcing we mean some sort of upward motions that are occurring well ahead of the front here that are going to have a chance of producing maybe an isolated storm ahead of the main line of thunderstorms. And that's something that you typically look for on a potential squall line event. Is there enough forcing ahead of the squall line to produce an isolated supercell that might have a chance of producing, say, a significant tornado? And if you've got no prefrontal forcing, then pretty much all of your storms are going to be purely linear. If you don't have any forcing occurring ahead of the main line of thunderstorms, then all the thunderstorms are just linear. You don't have any isolated thunderstorms at all. Now, it's also something kind of important to keep in mind that in quite a few severe weather events, it's never a question. You're going to have some degree of linear modes, but you're also probably going to have some degree of isolated modes. But you might have a nice setup where you have a mix of modes. That means you might have roughly the same amount of linear modes as you do isolated modes. So that gets into sort of a gray area, literally. Where you might have some factors favoring isolated modes and some factors favoring linear modes, where instead of getting pure lines of storms or purely isolated storms, you might end up with a mix. You might end up with a mix of linear modes and isolated modes, which can result in both a tornado event and a damaging wind event potentially if the atmosphere cooperates. But typically when you get mixed modes, you just have to start worrying about both tornadoes and damaging wind equally. But if you have more isolated modes, you probably are going to be worrying more about tornadoes. You can get tornadoes with linear modes, but ideally for a high-end tornado event, you want isolated thunderstorms. That is, those isolated supercells that can produce strong to violent long-track tornadoes. And for a damaging wind event, ideally you want linear storms. But this is probably the trickiest part of any severe weather forecast, is determining whether you're going to have isolated versus linear modes, because this part right here is pretty easy to diagnose. It's pretty easy to tell if the flow aloft is perpendicular or parallel to the boundary. The part that's not so clear-cut is the amount of forcing. Trying to determine how much vertical motion is in the atmosphere is something that's very challenging. And it's not something that you can directly observe from, say, a sounding. You can't launch a weather balloon and measure how much vertical motion is present at each level in the atmosphere, because the balloon itself is moving upward and it has no way of measuring any sort of vertical motions. So you have to infer what the vertical motions are based on characteristics of the environment itself. And part of that gets into something called quasi-geostrophic theory, which is something you'll cover in your senior year. But that's pretty much the one thing that makes this forecast so challenging, is trying to determine a state variable that you can't actually observe directly. That's what makes this process so tricky. You can't directly observe how much vertical motion is present in the atmosphere. You can only make an educated guess as to how much vertical motions are present in the atmosphere. But I think that's going to do it for this segment on linear versus isolated modes. And so that's going to do it for lecture 23. Hopefully you found this at least somewhat enjoyable. And that's also going to pretty much wrap up the severe weather unit. So hopefully you got learned some really interesting things from that. So that's going to do it for lecture 23. So with that, I will see you all in the next lecture, where we start discussing a topic related to the atmospheric boundary layer. So I will see you all there.